capacitances of this is 10. So these inverters will be of size 10. Now, these lines are going to the different NAND gates in a 4-input NAND gate followed by another inverter over here. So they will be having some, capacitances depending on these lines over here. Now this word line is going across the 32-bit lines, and each bit line has a 3 unit of capacitance. So 96 units of word line capacitance is corresponding to these driving over here. So your goal is to find out what should be the sizes of the inverter over here, what should be the sizes of the NAND gate over here. This, of course, we know the size is 10. So as a designer, you'll have to find out how many stages to use, how large each gate be. I mean, this is of course given, but there could be other alternatives. So as a designer, you should look into other alternatives, that how many stages to use, how large each gate be, and how fast the decoder will operate, right? So these things you have to find out. So let's run the example for this particular case. Now, using this formulation, what we showed over here, how do you size the size Z and Y? So that's shown over here. So the electrical effort H is equal to, we mentioned that this word line is 96 units, 32 multiplied by 3, and this is 10. So H, capital H is equal to 96 divided by 10, 9.6. And that's what it is, capital H. Each of these line is going to half of this. So there are 16 of them. There are 8 lines over here, and each NAND gate takes 4. So the branching effort on each of these lines is 8. So that's what we write over here. Branching effort is 8. Each NAND gate is 4 input. So n plus 2 divided by 3 is equal to 4 plus 2 divided by 3 is 2. So that's what we're writing over here, 2. So now I can calculate F is equal to GBH is 153.6. There are 3 stages. So each stage has a stage effort of 5.35. So I can calculate the optimal delay from the input here to the word line going to all these places, to all these bit lines, right? That is equal to, we calculate by finding out the stage delay f.35. There are 3 into f is, and each NAND gate has a parasitic delay of 2, and then the other gates have got 2 actually. Sorry, I mean this is a 2-input. This is a 2-input NAND gate, and then there are these gates. So altogether, we'll have a delay of 2 inverters is parasitic delay is 2, and 4 input NAND gate, the parasitic delay is 4. So altogether 22.1. So for this particular example, without doing any simulation, I'm trying to find out the figure of merit of the design, and the minimization of the delay is the prime objective. So that is 22.1. So I have done that. Now I select this one, I've not made that decision. So before I come back to this, let me find out what are the other alternatives. If I use NOR gate, then the delay in a similar way will be 234. If I use NAND4 and inverter, it is 29.8. That is single inverter, right? I told you that if I add inverter, I can reduce the delay. NAND4, inverter, NAND4 inverter, 22.1. So this is what it is, that here I have 3 stages, here I have 2 stages. The overall delay is higher here than here, inverter, NAND4 inverter. Now if I use another inverter, NAND4 inverter, that is 1 to 4 stages instead of 3, my delay reduces further. If I use NAND2, not to inverter, it reduces further. And the best one is NAND2 inverter, which I showed last time. So in this particular example, for your register file, you should not use 4-input NAND gate or NOR gate. What you should do is that you should use A, B, C, D, inverted. This is our A, B, C, D, and G is equal to A, B, C, D. So this is what is this one, NAND2 inverter, and this is the best delay. Okay? So in your design, in order to reduce the delay, you should use this configuration. Now, just to finish our discussion, if we end up using this, because many times if you try to synthesize, your synthesis tool will try to use something like this. Sorry. So how do I then size the transistors? Sizing the transistor, we use the same technique. So here it is 96. So the input capacitance over here will be, output is 96. Input will be given by that formula, C out Z multiplied by G in of this divided by F. F is equal to 5.38. So here we'll have an input capacitance of 18. So input capacitance over here is 18. So what should be the size of the NMOS or PMOS transistor? PMOS is 2 times larger than the NMOS. So the NMOS will be 6 and PMOS will be 12 for the inverter. Now we go back, use the same formula to find out the capacitance over here. C in at Y is given by C in Z over here divided by Z4 multiplied by G4 divided by F. So here it is 18. The logical effort of 4-input NAND gate is 2. Stage effort is 5.38. So the capacitance over here is 6.7. Now we know that in the case of 4-input NAND gate, we have 4N of the NMOS transistors, and PMOS transistors are 2N. So this will be NMOS transistor will be 4.4 and PMOS transistor will be 2.1. Together, they will provide the capacitance 6.7. So this is how you size the transistors of the different gates. Is it clear? Is it clear? So, don't ignore this, because ultimately, when you go out, you'll have to apply these techniques. Similarly, for the inverter over here, we can find out that the branching factor is 8. So we use the formula, the input capacitance Y is 6.7, then inverter logical effort is 1 multiplied by the branching factor 8 divided by the effort of each stage is 5.38. So we get 10, and that's what we wrote over 10. So the input, for the inverter, the NMOS transistor will be 3.3 and PMOS transistor will be 6.6. Another example, 8 input NAND gate. Tell me which one is the best example here. Out of 3 choices, which one will you use? Number 7. 1, 2, 3, 4, 5, 6, 7, you.
C is best.
Shall I use this?
C.
Huh?
Third one.
Third one? Okay, how many of you are in favor of third one? 1, 2, 3, 4, 5, 6, 7, 8. What about you? Yours is
C.
3. Okay. Between these two, which one? Which one? 2. Because you see the formula here, right? This is 3.338, blah, 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 blah. So this parasitic capacitance is much larger than this. So both being identical, so I will choose this. So